Hello, friends. Welcome to Hydraulics and Hydraulic Machines class. In today's class, we focus on the last part of the theory of the impact of free jets. In the impact of free jets, if you just recollect, fixed plate vane version is one, then moving plate, single plate is version number two, and that portion we concluded with unsymmetrical vane where we have drawn the velocity triangles also. And we concluded that single plate or vane moving is not practically feasible and that is not an application at all, and that leads to the series of plates or vanes mounted on a wheel. So in all these cases till now, if you remember, in the series of flat plates or vanes, the jet is striking at the center of the plate or the vane. So, but the difference is from a single plate moving to the series of plates moving is only one difference. In the single plate moving, the whole mass will not strike the plate, whereas in series of plates, the whole mass will strike the plates. The reason being, in the first case, the plate moves away, but in the second case, as the first plate moves in, the second plate comes and occupies its position. Thereby, there is always a plate before the jet. So that's why that mass is the only difference. Apart from that, the entire derivations in the case of moving plate and series of plates, moving vane, series of vanes are all same. But the last part of it is what that is actually what is the force exerted in the case of series of vanes mounted on a wheel where the flow is striking at one end and moving into the other end. So that means when the jet strikes at the center, it is tangential flow. That means the flow is tangential. If you take from the center of the wheel, the flow, if you take it, it is at the same distance. Whereas in the present case, which I am discussing, the flow enters at the outer periphery of the wheel and leaves at the inner periphery, or the flow may enter at the inner periphery and leaves at the outer periphery. That means it is not tangential, it is radial. The flow is towards the center or away from the center. So that is why we need to do again this separately. So kindly remember, when the jet strikes at one end in the case of series of vanes and leaves at the other end, the flow is not tangential. The flow is moving radially towards inside or radially towards outside. So this how to solve it actually, this type of problem how to solve it, because whereas in previous case the jet is at a constant distance from the center, that is why it is tangential flow, whereas now it is not equal distance. The distance from the center to the outer edge is separate, the center to the inner edge is separate. So when both are same, the velocity of vane at the inner side, outer side, both are different. So all the things are going to be different. So this case we will study. Right? Now, once this case is studied, then I will explain where what is the tangential flow, what is that radial flow, where this application is used, where that application used in the coming chapter of turbines. So that concludes us the theory part of the impact of free jets. In this lecture, we focus on the derivation for force Work done. In case of series of veins, right? So what is it? Let us study. So this is a series of curved veins, radial curved veins, right? So what the jet of water enters here and leaves here. If I take the center of the wheel is somewhere here, right? If I take this distance and if I take this distance, this is R1, this is R2, because I mentioned this as inlet, this as outlet, right? This is like this. There are series of veins are like this. Like this number of veins are there, right? So only one vein I have taken for my problem, right? This is now if I take it, flow is entering here and moving towards the center. When flow move towards the flow is towards the center. So this is called as radially inward flow. If the flow enters here, if this becomes inlet and this becomes outlet, then naturally radially outward flow. So kindly remember that. So if this is the general first figure, now what I will write, consider a series of radial curved veins mounted on a wheel as shown in figure. Okay, that is what I have shown to you. This is the first thing. Now, next is what I will try to draw basically where the jet is striking the jet of liquid impinges. Impinges means strikes upon the veins and the wheel starts rotating at a constant angular speed omega. This we have taken it as omega. And now what is R1? R1, R2 are the radial distances from the center of the wheel. As R1 and R2 are different. The tangential velocity of the vane, the tangential velocities of the vane at inlet and outlet are different. Therefore, U1 is equal to omega R1, U2 is equal to omega R2. This is first thing. Then the flow system is inward or outward, depending upon what? Whether inward means where the jet head should enter at the outer periphery. Whether the depending on whether the jet enters at outer periphery. Outer periphery entering means automatically it is leaving at the inner periphery. That is what we call it as inward or inner periphery. When the jet enters at inner periphery, that is, it means it is moving outward. So now what are the inlet velocity triangles? I can show it in the figure itself here for your sake. Then I will draw clearly, neatly afterwards. So I will just like previous ones only. If I take it actually here, and if you take this is the tangent here, right? This is how V1, and this is how because it should be parallel to here U1. So this should be VR1, right? And if I take this, this should be VW2, and this is VF2, and you know V1 is alpha here, theta, right? Here how it flows, if I take it, this is how it flows. Directly it is VR2, right? Then this is U2, then this is V2, then this will be VW2, this is VF2. In the case of radial things, this it should be exactly perpendicular like this, right? And this direction is here. So this is phi, this is beta. The inlet and outlet velocity triangles are as it is, whatever we have learned. Only thing is this is the tangent here and this is the tangent here. That's all. Rest of the things are same. Velocity triangles, there is no difference. But only thing is, in the previous cases, the distance between the center and the jet is same. But now, actually, it is different. So that's why this U1 is different, U2 is different. Now, how to going to solve the problem? So once again, if I take it basically, so if this is your radial curved wave, right? This is the inlet part, right? This is the tangent part. So this is how V1, U1, VR1, right? Then taking it, this is these are the vertical and VF1,
VW1. This is alpha, this is theta. Alright. Then the outlet velocity triangle, if I take it, this is the vane part, right? So this is the outlet if I take it. So this is the tangent. So now if I take it, this is VR2, U2, V2, VW2, VF2, 5 feet. So this is inlet velocity triangle. This is outlet velocity triangle. So this is the case. If I take this, now what is the first thing? Mass of water, mass of liquid, striking per second. Because it is series of veins, whole mass will strike. Please remember, in the previous case, one single vein is there. Instead of V1, we have written here VR1. Please note that here the whole mass will strike. So that's why it is rho A V1. Why? Because rho A V1 in brackets, series of veins. Right? Next. What is the momentum? Mass is known, so therefore momentum of liquid striking the vein per second at inlet is equal to mass into velocity. What velocity? That mass into velocity. So velocity should be perpendicular. So it is rho A V1 into VW1. It is the component, horizontal component of absolute velocity because it is the perpendicular distance. When we are taking it, the perpendicular thing I should take it. This is how it is going to be rho A V1 into V. Then momentum of liquid striking per second at outlet is equal to rho A V1 into this into we should write it as VW2. Right? When I write VW2, I will use minus. Why minus? The minus sign indicates VW2 is in opposite direction. Now V1, if you see, this is how V1 actually. So that means in the direction of on the horizontal direction I am taking. So whereas here this is V2 is in this direction. So this is VW1 direction. This is VW. So that's why that minus we have put it. Then if I write it, what is VW1, VW2? If that, let me put it. Then afterwards, what is angular momentum per second at inlet is equal to, right? Momentum into radius. So radial distance or radius, this you can call it as radial distance. So momentum is what? Rho A V1 into VW1 into radial distance is R1. So angular momentum at outlet. Why all these things I am doing it is the reason that there is no way straight away you can get force because the wheel is rotating. It is not at constant distance actually. The jet is not at the constant distance from the center of the wheel. Jet is entering at the outer edge and leaving at the inner edge. So when it is that is the case, then the velocities both are different. So that is why actually we need to use the angular momentum principle and then move ahead. Whereas if it is tangential, I will use directly the impulse momentum equation. As the flow is radial, automatically we need to switch over to the angular momentum principle. Minus is very important. So, angular momentum principle, what it states, torque is equal to, because angular momentum principle talk it talks about torque exerted by the liquid on the wheel is equal to rate of change of angular momentum. This is the principle. So therefore it is initial angular momentum per second, initial angular momentum per second minus final angular momentum per second. So therefore, what is initial angular momentum? It is rho A V1 into basically VW1 into R1 minus rho A V1 into mass will not change into minus VW2 into R2. Right? If I take it, it is rho A V1 into VW1 R1, right? Minus plus VW2 R2. That, that is where I will start. Then once angular moment torque is obtained, what is work done per second? Work done per second is equal to torque into angular velocity. So it is equal to rho A V1 into VW1 R1 plus VW2 R2 into angular velocity omega. Therefore, if I take it inside, rho A V1 into VW1 into omega R1 plus VW2 into omega R2. Rho A V1 into VW1 into what is omega R1? U1 plus VW2 into omega R2 is U2. So this is what we got actually. In the previous case, if you see the tangential, basically the flow is in tangential direction. U1 and U2 are same. So automatically I have taken it outside and put it as U. Otherwise, the equation is simple, same. Only thing is, instead of rho A V1 in the unsymmetrical vein, we got it as rho A VR1. This VW1, VW2 common only. Instead of U1, U2, it is only U which is outside. But in the case of radial basic veins, in the case of radial veins, what principle we have used? It is the angular momentum principle. In the angular momentum principle, how the calculation is torque, and from torque to work done per second. While calculating the torque, what are the steps? Initial, basically, momentum. From there, angular momentum. Then torque leads to work done per second. So this is the case. So now again, let us write the final thing. What is work done per second is equal to rho A V1 into VW1 U1 plus VW2 U2. This is what we got. If beta is less, this equation is valid if beta is less than 90. If beta is equal to 90 degrees, right? And this case is called as the discharge is radial. This is called as the discharge is radial. Discharge radial in any problem means beta is equal to 90. In such a case, work done per second is equal to rho A V1 into, therefore here VW2 is equal to 0. Therefore, it is VW1 1. So then if beta is greater than 90, then work done per second is equal to rho A V1 into VW1 U1 minus VW2 U2. So this is the thing. Then if from the work done, if you want efficiency is equal to work done per second by kinetic energy of jet. So which is nothing but rho A V1 into VW1 U1 plus or minus VW2 U2 divided by half into rho A V1 into V1 square. So this is the thing. So rho A V1 you can cancel. So this here it is eta is equal to 2 into VW1 U1 plus or minus VW2 U2 divided by V1. So this completes. So I wish to conclude this chapter with some note actually. What is that note? Please take seriously about this note. Number one, what is tangential flow? Distance of liquid particle of liquid or in brackets jet from the axis of rotation remains same as the flow takes place to the veins, right? In such a case, in such a case, impulse momentum principle is used. This application is Pelton turbine, like a radial flow, distance of liquid, that is jet, from the axis of rotation varies along the path of flow. Here, in such a case, angular momentum principle is used. Application, Francis turbine, centrifugal pump. So this is the thing. So here in this case, we calculate torque from torque to work done. Here we calculate force to work done. The difference is this. In the case of tangential flow, distance, for example, if I want to show the figure also, I will show. Suppose if you take this is the wheel. This is the axis of rotation is this. The vanes are like this. Jet strikes here. So if you take the distance from the center, this is same. This is tangential flow. That means if I draw a tangent, this is the tangent. So this is in the case of radial flow, this is how this is the center. This is how it looks. The wheel, this vein is like this. This is the vein. right? The water, this is the called as outer periphery, and this is inner. So it enters here. If I take it, this distance is R1 and this distance is R2. So both are different. So enters here and leaves here. So this is radial flow. R1, R2 are different. So exactly flow takes place towards the center like this. Here the flow is tangential. So that's why it is tangential flow, it is radial flow. This application is Pelton turbine, this application is Francis turbine. So that actually we will take in the future classes. Here I will stop.
So, in this lecture, we have found out how to solve a problem or how to derive the equation for work done in case of the flow is radial. It enters at the outer periphery and leaves at the inner periphery. Of course, the opposite is also possible. It enters at the inner, leaves at the outer. This case we have solved. This type of problems, radial flow problems, can be solved only by using the angular momentum principle. And in the case of angular momentum principle, we don't get a force directly, we get the torque actually. From the torque, then we will get what is we call it as the torque into angular velocity is equal to work done per second. There, in the case of tangential flow, we calculate force and multiply with the velocity of the wind, we get work done per second. So this is the difference. So we have shown otherwise velocity triangles, everything is same. Only this is the difference. Thank you. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.